Hello. Um, this is about dimensioning holes. So a leader should point to the view, the center view of the hole if possible. Okay, so what we're talking about here is we have a radius here, and the leader for the radius points to the center of the radius. Okay, over here we have the radius is defined. No, it's not pointing to the center. We want this leader here with the arrow to point to the center of the hole. Okay, so what we have here is these metric holes here. We have the dimensions for the hole, and then we have this leader, and it points right through the center of the hole. That's how we put a leader for a circle. Countersunk, counterbore, spot face, and tap holes are usually specified by standard symbols or abbreviations. So in this case, we have the V as the countersink, and then we have to have, and we're going to talk about these a little bit later. I'm going to talk about this in depth in another lesson. So dimensioning rounded end shapes. Okay, so what we're looking at here is just kind of like a link with two holes in it. So how to dimension it? Well, all we really need is this dimension here, which comes from the center of the two holes. And then we have the radius dimension. And then because we have the radius dimension, it tells us what the overall width of the part is. So if you look at this part here, everything is dimensioned in this view. I mean, other than the thickness of the part. You have the two hole sizes, you have the radius on the outside, and you get distance between the hole. Everything else is defined. And that's kind of like what we have here. If you have a slot through that hole, the same thing. All we have to do is dimension these radiuses and then the distance between the arc radiuses. And then in this case, the 20 is kind of like a double dimension because you already have this R2 right here. Okay. Now, how to dimension chamfers. Okay. A chamfer is a beveled or sloping edge. Several ways to do it. We have the length of one leg, 3 millimeters, and then we have the 30-degree chamfer. Or the other way to do it, in this case, we have 3 by 30, or if it's 3 by 45. But if it's 3 by 45, we know that both legs are 3, so therefore we could say 3 by 3 chamfer. Dimensioning keyways. So what we do on a keyway is we dimension the width of the keyway. So we got to have that keyway has got to be on the center line of that cylinder. Okay, so we have the overall width of the keyway. And then we have half width of the keyway that goes to the center line. That's how we dimension the keyway has to be at the center of the cylinder. And then we dimension the depth of the key to the bottom of the shaft. Okay, it's very important. So from a key seat like that, it's from the depth of the key seat to the bottom of the shaft. Now, if we're talking the opposite, stock keys like this, again, we have the key. This would be like the hub feature. This would be like the shaft. So we have the width of the key. We have half of the width to say that this will be on the center of that cylindrical feature. And then we have this length here, which comes from the opposite side to the depth of the key way. So that's how we do it. Okay, dimensioning knurls. So a knurl is a roughened feature. We're going to talk about these a little bit more later, but hang on a second. A knurl is a roughened surface to provide a better hand grip to use as a press fit or as a press fit. Typically, you'll see these like on micrometers. It's just the knurl allows you to give more of a tactical feel. So these would be the ways to dimension a knurl. And then you also have to locate all holes and sizes of features, okay? So in this particular case, these are location dimensions of features. So we have a slot here, a rectangular, well, it's actually a plug that sticks up. And how do we locate it? We locate it with extension lines and dimension lines from the edge of the part. And same with this hole here. We have a hole, and we use the center lines for the hole to dimension where that hole is located from the edge of the part. Again, we like to see, when we're dimensioning holes, we like to see this dimension in the round view of the hole, or the contoured view of the hole. You want to see this dimension here. You don't want to see that dimension over here, because you can't see it's actually for holes. I mean, and the reason for doing this is for readability. When you're looking at this, you can say, oh yeah, this 38 millimeter dimension is the distance between those two holes. It's very clear, it's very plain. So that's how we want to do it. Here's a coordinate dimensioning. Okay, so everything's kind of like a baseline here. So we have the 0, 0 point as our baseline. And essentially every point on here has a coordinate. Okay, so what we've done here, this is a coordinate dimensioning system. You don't always have to use the coordinate dimensioning system in some parts, like sheet metal parts. It would be beneficial to use the coordinate measuring system, but typically for not all parts. So what we have is we have different types of holes. We have those holes are listed over here with leaders, and those leaders point through the center line of the hole. So we have 8 of these holes with 406 through, with a counter bore of 1 inch to a depth of 562. Then we have 16 of these little tapped holes, quarter 20, and then we have 4 of these 1032 holes. Okay, so these dimensions are the coordinates of where those parts belong. You can imagine if you're programming a NC machine to do this, it would be pretty easy, because you look at these dimensions and the coordinates, and that's how you program your machine tool. Another way to do this is tabular dimensions. Okay, so what happens here is this is done a lot with tool design. So we have the screw here, and then for different tools, for instance, they use different sizes of these things. Some of them have different threads that they're made out of. Some of them have different overall lengths. This is the overall length. B would be the thread diameter. C is the head diameter. So what we have here is we have one little simple drawing, but by using details, we have 5 different parts are actually detailed with this. So this is used a lot in tool design. It's probably not something we're going to see too much in this class, but it's a tool, and it's something that you could use for your drawings if you needed to. So for dimensioning for numerically controlled machines, each part has 3 mutually perpendicular datum planes, and then these planes must be obvious or clearly identified. So that's how we would do that. And then machine pattern or forging dimensions. Frequently a dimension that is convenient for the machinist is not convenient for the pattern maker. So typically what we have to do is we'll have forging drawings, and we're going to do this in our projects towards the end of the semester. We'll learn more about machining versus forging drawings. So it's not necessarily applicable right now. And then finally, notes. It is usually necessary to supplement the direct dimensions with notes. Notes should be brief and carefully worded. We're going to talk more about notes specifically later. Okay, so this is your lesson 2. Good luck on your assignment. Thank you.